All right, let's get started here with example 4. It says water runs into a conical tank at a rate of 2 feet cubed per minute, and the tank stands point down, has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Now, to save time, I have drawn the picture. Let me explain what we have. We have a cone with the point down. We have water flowing into it. We have a base radius of 5 feet. We have a height of 10 feet. And there is water filling up in the cone. Now, the dimensions of the water are the items that are variable. We have the height of the water and we have the radius of the water, both dimensions which are changing as we fill up this cone. So let's write out the information given to us in the problem. dV dt of the water is 2 cubic feet per minute. Our next dimension is dH dt. Okay, and this is of the water. You can put a little W there if you want to, just so that you don't forget. And that's what we don't know, but we want to know what it is when the height of the water is equal to 6 feet. Okay, so that's everything that the problem gives to us. All right, so let's think about the relationship or the equation that will tie all of these quantities together, and it's going to be a volume of a cone equation. So again, we got to dig deep into the recesses of our mind. What is the volume of a cone? It's 1/3 pi r squared h. Okay, great. So let's just take a quick check. Volume, we have radius, and we have height. Okay, but here's the thing. We kind of have too many variables. So we have a dV dt. We are going to end up looking for dH dt. What are we going to do with this r? Because that volume, that radius is changing, if we were to take the derivative, we would end up with a different rate. We really don't know that rate. However, we can write an expression for radius based off of the picture that we have. So what I'm going to do here is, another geometry type of skill. I'm going to draw myself some similar triangles here because I can write a relationship for the radius of the water based off of the height of the water and the height and radius of the cone. Okay, so right now this is what we know. And these values are all proportional to one another. So we can use the similar triangles to do this. So, all right, I'm going to write myself a proportion. So then I can say that my radius of the water and the radius or the height of the water is proportional to the base radius of the cone and the height of the cone. All right, so this relationship is one of the relationships that I could write. We could change these variables around and still end up with the same relationship. But we need to write ourselves an equation for r. So we're going to solve for r, multiply by h. So we end up with r is equal to, well, 1/2 h, or just h divided by 2. Okay, so this is the expression that I'm going to use for r. Okay, let's plug it in. So volume is equal to 1/3 pi h divided by 2 squared times h. Let's clean this up. V equals 1/3 pi h to the third over 4. All right, so let's take our derivative with respect to time, d dt. So then we have dv dt is equal to, well, 1/3 pi, all of that is just like a constant, so it'll stay. We will multiply that times 3, and then we have this, actually another constant of a fourth right here as well. So the 3's will cancel, and then we're just left with 1/4 pi h squared dh. dt. Okay, so let's take a quick variable check, make sure we have everything that we need. So dv dt we know. Yes, dh dt is what we are looking for. And it says when the water height is 6. So we know that also. Let's plug it in. Our dv dt is 2 1/4 pi 6 squared dh dt. And this is 36 divided by 4, so that's 9. So that's 2 equals 9 pi dh dt. And so this is what we end up with, 2 divided by 9 pi. And our unit is going to be feet per minute. That is the change of the height of the water over time. There you have it. Let's move into example 5. It says a hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so let's draw ourselves a picture. So we have the horizontal ground. And then we're talking about a balloon rising up. And let's just make ourselves a basket balloon. All right. So this is as a Y here. This is some kind of X. And then it says a rangefinder. So we'll say this is a rangefinder over here watching the balloon rise up at a particular angle. Okay. So we can kind of see what's happening here. That angle, we'll call it theta. And it says here, oh, what else do we know? That rangefinder is 500 feet away from the liftoff point. At the moment, the rangefinder's angle of elevation is pi over 4. The angle is increasing. Okay, so we do know a d theta dt. The change in that angle is 0.14 radians per minute. We do know that. And then they want us to find how fast is the balloon rising. So we want to know what is the change in the y when. So what is this when our theta is pi over 4? So that's everything that this problem has told us. Okay, so it looks like we have an angle, we have an x, we have a y. I think we're going to have to use a trig function. That is what's going to tie all of this together. Okay, so this is what we have. So I have an angle, and I'm talking about x and y, and I'm not dealing with my hypotenuse at all. So then the trig function of the hour is going to be tangent. Tangent is going to be defined as opposite over adjacent. So this is the equation that's going to tie everything together. All right, well, so now that we have our picture, we have our equation, we've identified everything, we know what we want. Well, let's go ahead and take the derivative. But you know what? Let me just change this up a little bit. I want dy dt, so I'm going to bring that x over. So I'm going to rewrite this as x times the tangent of theta is equal to y. That's just going to make my derivative a lot better because nobody's got time for doing quotient rule and all that kind of stuff, right? Okay, so d dt. And let's go for it. Well, so my x is not changing. So this is really like a constant in front of tangent. So I don't have to do product rule. Yay! Okay, great. So let's leave it. So we're going to have x the derivative of tangent is secant squared theta, and then d theta dt equal to dy dt. Perfect. There it is. So now let's talk about plugging everything in. So the x that we have, okay, so that's 500 feet. We do know that. Secant of our theta, and our theta is pi over 4, okay, and d theta dt, we know they gave us that also. All right, so let's just plug all of this stuff in. So we have 500 times the secant squared of pi over 4. D theta dt was 0.14. All right, so we have that also. And that's going to give us our dy dt. Well, wait a minute. So let's do a little bit of trick here. What is the secant squared of pi over 4? But let's just remember. All right, so pi over 4, if you recall, it's like a 45-degree angle, right? Coordinates here are square root of 2 over 2, square root of 2 over 2. Okay, secant is the reciprocal of cosine. So it doesn't matter actually whichever one it is. It's just going to be square root of 2 over 2. So secant at pi over 4 is going to be 2 over the square root of 2. And then we need to square it. So then that just becomes 4 over 2, which is just 2. Okay, great. Let's plug it in. So 500 secant square. Oh, we already know what that is. So that's 500 times 2 times 0.14 is equal to dy dt. So that's 1,000 times point. Okay, great. So this is 140, and our unit, feet per minute. That is how fast the balloon is rising at the moment. Okay, here we go. Last example. Example 6. A police cruiser approaching a right-angled intersection from the north. Okay, so we're talking about intersections in north. So we've got ourselves a grid here. So approaching a right-angled intersection from the north. So that means he's coming this way. Is chasing a speeding car that has turned the corner and is now moving straight east. So the car is now moving this way. And when the cruiser is 0.6 miles north of the intersection, so this is kind of where my police cruiser is. So this is a distance here of y. The car is 0.8 miles east, so that's over here. So this is some x distance to the east, and the police determined with radar that the distance between them and the car is increasing at 20 miles per hour. So that's this distance here. And if the police cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, so let's just write all this out. So what we know is that the distance between them, it says, is increasing at 20 miles per hour. Then dz dt is 20 miles per hour. If the cruiser is moving at 60 miles per hour, so the cruiser is moving in the y direction and specifically negative, so dy dt, negative 60 miles per hour. What is the speed of the car? So that's going to be dx dt. And that's what we want to know. And we want to know what it is specifically when our x is equal to 0.8 and when our y is equal to 0.6. Okay. So once again, we have this right triangle situation. We are not dealing with any angles right now. So this is going to be Pythagorean theorem again. So we have x squared plus y squared equals z squared. Okay. Let's go ahead and take the derivative with respect to time. So we have 2x dx dt plus 2y dy dt is equal to 2z dz dt. Okay, so let's just take a quick check and make sure we have everything we need to plug it in to find dx dt. So the one that we're looking for is here. All right, we know the value of our x, we know the value of y, we know dy dt, we know dz dt, but we do not know what the value of z is at this particular instance. So we are going to have to do a side calculation again with our Pythagorean theorem. So x squared plus y squared equals z squared. So we have 0.8 squared plus 0.6 squared equals z squared. Okay, so these numbers actually seem familiar. This is kind of a Pythagorean triple. So when you solve this out, you end up with z is equal to 1. Pause the video and do it yourself if you don't believe me. But okay, so we got z is equal to 1. So now we know what our z is. Great. So let's plug everything in. So we have 2 times our x is 0.8. dx dt is what we're trying to find. Plus, we have 2 times 0.6. dy is negative 60 miles per hour. Equal to 2 times 1 and 20. All right, there is everything all plugged in. Go ahead and solve it. See what you get. XDT, math magic in there. And you should get that the car is traveling at 70 miles per hour. So if he's on an intersection, I don't know what the speed limit is on this road, but he is going 70 miles per hour. There you have it. Thank you so much for watching. Now let's get into some practice problems.